Hello, welcome to this channel. I believe this has become a cliche, and it's your guy, the Bromtech designer, and today I'm going to take you through the design of a beam in Prokon. You hope you remember we did this beam. We determined the load takedowns manually, and I hope you remember me showing you this document, structural design guidelines. We explained that, and then we did load takedowns for these slabs. We decomposed our loads to the beams, and we decomposed loads to beam D, and thus we came up with this diagram, and we were able to come up with this. And if you have not watched this video, you can go to the link below. The link to the video has been attached, so that before you design in Prokon, you understand how first of all do you decompose these loads to come up with such a system. So we are going to use Prokon to design these, to analyze and design this beam. Join me, and Prokon is here. We have opened it. We need to wait for a few minutes. What can we be doing while waiting? We can sing. Oh, how I love Jesus. Oh, wow. Before we finish the song, our Prokon is here. Yes, we're using Prokon 5.0, and I have already explained the introduction to this in a different video. So right away we're going to the beam, and you remember we are doing a concrete beam, a reinforced concrete beam. If it was simply supported, you can use this single span beam to just do analysis, because this does no design. This is purely for analysis. Or if you could have wanted it presented in 3D, we could use a frame or sumo. And if it was a beam on elastic support, the same way we do strap beams in our foundations, we could analyze it with this. But for this, it is a concrete beam. So for concrete, you proceed to concrete. Once you get to concrete, you open continuous beam, and then on continuous beam, these appears. The first thing I would love you to know is, if you're designing and you're new here, and you don't know what to do, you can watch a tutorial like this one. Or option number 2, you could select one of these examples and find out what has been done. But a disclaimer is, whatever values have been entered here are not correct values. They've just fed values so that you can see the way values are supposed to be fed, so that you can also do the same. So if you want to learn what are the individual entries to make, you could watch this, or get somebody to guide you. For this input, the first input of FCU, this is the class of concrete, and we can going to change it to 25. We've changed that to 25. That is the class of concrete we're going to use. FY is the grade of my steel, and the steel that is readily available in the market is the one that is 500 MPa. FYV is the steel of my links, and I'm assuming I'm using round bars. I'm not using deformed bars. The strength is normally 250, and they are plain. And the next one is percentage redistribution. In Prokon, sometimes I'm required to redistribute the moments that are applied, either downward or upwards. Therefore, here is where I enter the fraction of moment that I want to be redistributed. And for the method of redistribution, it can be either downward or optimized, and I can either do D or O. Those are the only options here, though in most cases I do not do this redistribution, so I leave it as 0. So whatever you enter here, as long as this is 0, you're good to go. But if you want to redistribute your moment, this is where you do that, and you tell us whether it is downward or optimized. Next, we have the top and bottom cover, and they have included the word center. Now, this cover is not just the concrete cover you provide on your section. It is concrete cover, and you add half the dimension of the bar that you're considering when you're getting this cover. So the top cover is the distance from the top surface to the concrete center of the topmost steel. And the bottom cover is the distance from the soffit of the bottom to the bottommost the center of the bottommost steel. So if I'm using 20 millimeter bars, half that diameter is the radius, which is 10. If I'm using a cover of 20 for my beam, then I'm going to use 20 cover plus 10. 10 is half the dimension of that bar, because remember we are taking the distance to the center of the bar that is extrememost. So I'm doing 20 millimeters cover and then 10, that is 30. So 30 is not the cover, 30 is the cover plus half the bar diameter, the bar you're considering as the one that is towards the surface the most. So for the bottom reinforcement, I'm also going to do 30. If I do a cover of 30, that means I'm going to do 30 plus 10, that is 40, sorry. And then I also do 40 here. Disclaimer is sometimes you see I don't know the bars that are going to be in my beam. So this is normally just an assumption you're making, and you should make an assumption that from your experience that makes sense. For instance, this beam we are designing, we will use probably T16 bars or T12. So half of T16 is 8, and I've used 10 because I've assumed T20 bars. Therefore, I'm not far away off. I could even do 38 here. It is acceptable, yes. So, but I choose to go with 40. And then next you enter the dead load factor, which is 1.2, a live load factor 1.6. These are for the British standard. For the Eurocode, you do 1.5 and 1. For the Eurocode dead factor is 1.35, and this other one is 1.5. And then for the concrete density, it is 24. Though we are going to delete this. I'm going to have it either blank or 0. But I'm going to leave it 24 as at this stage, and you will understand why I don't want to have an input on my concrete density. And then you have percentage of live load that is to be considered permanent. This is where you enter. Sometimes you would wish to have a portion of the live load be considered as permanent, and this is used when calculating the creep components of the long-term deflection. So this is when you want the parameter to be used when calculating creep for permanent deflection or long-term deflection, then you should do that here. Though in this case, I normally do a percentage of consideration of 0, or basically 25 is not bad. You can also read this from the code, or if you have these other parameters, you can get your values from the graphs and you feed them here. And then next is the creep coefficient, and this is the 30-year creep factor that we use when we're calculating the final concrete creep strain. And this also depends on where your site is, your site parameters, whatever you want to consider permanent, and all these other things. So this is the coefficient that is normally a 30-year creep factor that we use when calculating final creep strain. And then lastly, in this window we have ECS. This is the 30-year drying shrinkage of plain concrete. And hope you know that creep and shrinkage of plain concrete are normally dependent on the relative humidity, as observed here. You have humidity somewhere, yes, relative humidity is right there. And then you have thickness of your elements, and the years is 30 years, and so on and so forth. So for these, you should normally leave them as default if you don't know how to get them from the graphs. And then you do the title. We can call it beam 1 design. It was beam D if you watched our previous video. So this was beam D design. Good. So once I'm done with this, you see this is the British code and this is the sans or sans, and I can change the code that I'm going to use in my design. I can come to design code. I go to file. Let me start afresh so that you can see. Go to file, design code, and then you can change the code you want to what you prefer. So if I wanted concrete Eurocode 2, I could have used this, but now I'm using the British standard. After I'm done with this input, I move to sections. Here is where I enter sections, and I can have as many sections as possible. Let's say I'm going with 3. And then for BW, you do the breadth of your structure. I'm doing a 200 beam. The depth, I'm doing 450. You see it appears there. Section 2, I can also do 200. And then I do a beam of 500. It appears there. For section 3, I can also do 200 or 250. And I also do a depth of 600 and all that. The reason why I'm picking these sections is sometimes you have beams with very long spans in some instances and short spans in some cases, and you might use 450 in some areas. Once it gets to the long spans, you increase it to 600. So Prokon allows you to enter different sections, but today we are going to use a uniform section for our element. And then you have all these factors. I'm just going to enter values arbitrarily so that you see what happens. Let's call these 200. And then the depth, we can call it a meter, that is 1000 millimeters. And then the BF top, let's do 50. And then you do let's do this 200. No, let's do that 200. And then for HF top, we can do that 50. BF bottom, you can do maybe 50. Just enter values arbitrary. Yes, you see, all these can help you in coming up with any shape, including H sections and I sections of beams. You can come up with them using all this. So during your free time, the first exercise is find out how to come up with different section sizes, including C sections, H sections, and all that from this dialog box. So I'm going to retain my 3 sections. After I've done my 3 sections, I proceed to my spans. For the spans, I need to consider the beam that I had. I have the first cantilever span, second, third, fourth. So spans are 4. How many supports? 1, 2, 3. And then I could assume these to be a support, but a cantilevered support. So I have 1, 2, 3, 4, 5 supports. And then spans are 4. So let me go back. Spans are the first span, second, third, and fourth. And then the section length, I'm going to enter my section lengths. This is 1.15. The second is 3.85, 3.05, and 1.3. So the first is 1.15. It is in meters. The second one is 3.8, I believe. 3.8 or 3.08. Let me check. It was 3.85, sorry. 3.85. The third one was let me see. The third one was 3.05. And then the fourth one lastly was 1.3. So I have my section length, and then I'm going to input my section numbers. Remember, I have 3 sections. Sometimes I can do different sections for different spans. I can do 1, 2. You see, this is more deeper than this. Sometimes I can even do the same section within different sections with different sections within the same span. And to do this, let me do maybe section 1 all through. Section 1 all through, you see. And then Prokon requires you to enter the section type on the left and the section type on the right. So I have decided when you do 1 on the left and you leave this blank, it is going to assume the same. But I can do 1 from the left and 2 from the right. You see, it is going to have section 2 starting, section 1 starting, and then they form some awkward funny shape there, which you will rarely find. The possible most applicable is having a section of different sizes in different spans. For instance, this is more deeper than the rest, but in this case we are using one section all through, and that was section 1. So section 1 all through, sorry, yeah. So sometimes once I have done my input on the left, I don't need to do the input on the right, it assumes the same. Now next is for the supports. For the supports, we said I have 1 2 3 4 5 supports. Therefore I'm going to put my support number 3 4 and 5. Now when it comes to the code, when it comes to the code as they have stated here, you have either C or F. The leftmost and the rightmost supports are actually cantilevered, and we can free them, because from our system they are cantilevered, we can free them. But if they were not cantilevered, we could have made them fixed. So by entering either C or F, we are either fixing a support by fixing it full, assigning it full rotational fixity, for example in beam and slab frames that are monolithically cast. And in this case our first one is cantilevered, so we put C, and our last one is cantilevered, so we put C. So you see they have all disappeared. The rest, if you enter F, they are just going to be fixed, or even if you leave them blank, it's going to be the same case. And then for D is the depth of the column that you are entering. B is the width of the column. So assuming I have 300, remember we stated the sizes of our columns, 300 by 300 columns. This is cantilever, so it does not have a column. So I'm going to the next. The next is 300 by 300, 300 again, 300 again, yeah. So those are my column sizes for support 2, 3 and 4, and I have been able to fix that. H is the height of my column. I could either input it or not, but by the fact that I have already fixed this and made these cantilevers, it does not matter the height of the column. The height will just appear when we are generating the drawings. So we can do a height of 3 meters. 3 meters, you see, I have done columns that are already below my structure. So I can also do the code in this case and do the columns that are above my structure. But you can observe that I have code F and P. Here a column can be pinned at its remote end by specifying P. If I specify P, it means I'm pinning it. And if I enter F or leave it blank, the column will be assumed to be fixed at that remote end. So let me leave it blank and continue entering my parameters for the top, now the top column. Yeah, 300, 300, 300. And then for H, I'll just do 3 meters, 3 meters, 3 meters. And then I'm done. So now for fixed or pinned, what I mean for these ones, it is at the remote ends. Look at what happens when I do P. You see, it becomes pinned at this remote end. So, but since we are not considering any moments from the columns, you can either fix them or make them remote. So we are going to leave that blank. And then that is when it comes to our supports. Next is when we get to loading. Now for loading, you see our system has been well sketched here. Now for loading, we normally use load cases when it comes to Prokon, and we could do load case number 1. Not 1. We normally do dead or live. You do D or L. and then here you enter a span. This is span 1, this first span. So what is my dead load for my span 1? You do enter a value on the left and on the right. Let's do this. This is a dead load was 5.55. So for dead load is 5.55. When I enter the same value, observe what happens. Dead, this is live load, no value has been entered, and then I have dead plus own weight. Remember I talked about density, and then when I'm loading, I've just put one load and it has done my own weight. But when we were doing the calculations, let me go back to this our previous study, we determined the own weight of our beams. Remember, we were determining the self weight of our beams. So the self weight has already been determined. That means I'm going to delete this to make it delete it. Just leave it blank, and once you come to loads, you see there is no dead weight. So if you used you determined your dead you permanent actions or your dead loads, including the dead weight, then you delete the density when you're entering parameters. Next, for my live load, I am going to pick from the same beam. That is 1.14, and then once I enter on the left, if I enter the same value on the right, it's just going to remain like that, 1.14. Sometimes I could even alter this. Observe what happens. It becomes a uniformly varying load, but in this case it is uniform. So if you leave it blank, it's the same. If you enter the same value, it's the same. A and B are the positions of my loads. If they are not entirely covering the same area, I could say it is starting 0.2 from the start and it is ending 0.4. It is ending at 0.4, and therefore you will have your UDL constraint within that point. But if I leave them blank, it means I'm going to have the same from end to end. P is my point load. Do I have a point load at this section? Let's see. Yes, I have a point load of 38.95. But now from observation you can see this point load is I need to enter either its value in terms of a dead load or a live load. Therefore let me determine whether I calculated that. This is section 1, I believe. Yes, section 1, it's here for section 1. And remember, the loads we are entering are loads that are not factored. I don't know whether the ones in this sketch are factored. This is 5.55. Let's find out whether it's factored. Where is it? Here it is. 5.55 is not factored, 1.14 is not factored, so we are safe. Let's go to the 0.1 point load. Here it is. Then total dead loads, it's 19.925 kilonewtons, and then for live loads it is 6.9 kilonewtons. So 19.925 and 6.9. So we should do 19.925, and then for live loads we're going to do 6.9. There you go. You have your point loads at the beginning of your beam. And then description, you can describe it whichever way you want. So this is dead loads, dead span 1, and then this is live span 2. Even if you leave the description blank, nothing will happen. Then we have again dead and live. These are for span 2. Span 2 has no well, I did not finished explaining this. A is the point where you are applying your point load. So at this A, if I'm applying it after, let's say 0.5 meters, you see it shifts to 0.5 meters. Therefore, I can still leave it to start at the beginning because that is where it was acting. For span number 2, for my dead loads, I'm going to do 20.51 dead load, 20.51, and then for my live loads, I will do 3.85. That is the second span, and you can observe that whether I enter the same values, let me copy this and then paste it on the right, it still remains the same, so you can still leave it blank or copy it. And then I had not also explained this. M is if I have any moment. I'm going to show that once I finish with these loadings. So we go to span 3. This is dead and this is live. And then for span 3, I have a dead load of 18.22. And then I have a live load of 3.05. And then for span number 4, I also have a dead load and a live load. For the dead load, the load is sorry for this. For the dead load, the load is 13.19 and the live load is 1.3. The load is 13.19 and then the live load is 1.3. I'm good. So what is remaining? This point load, the last point load. So it will be there. Let me get it. This is for span 4. It's just right here. This is 8.6675. 8.6675. Don't worry, I like using as many decimal places as I feel. So let this not worry you. So once I have entered this, you see it is modeled at the beginning of my span, but this is not where it's supposed to be applied. It's supposed to be applied at the end. So you get the span dimensions, which we had input here. It's 1.3. Then you do that 1.3 and it shifts towards the end. So the live load will still be at 1.3 and the load will be 2.6325. 2.6325. There you see, I have my point load at the beginning and the end, and then these center ones did not have a point load. Question: what happens when I have a secondary beam loading my beam at the center or which is not at the supports? That means that secondary beam is going to behave as a point load to my main primary beam. Therefore, at that junction, I'm going to have a point load. And here is where you get to the span and then you enter the point load value and both dead and live and the position where they're acting. What if I have a moment as a result of dead load? I could enter a value, let's say I enter a value of 10. Then you see I have this moment here that is going anti-clockwise. If I do negative 10, it will be going clockwise. Therefore, because and A is the distance, I can do even 1 meter. Then you see I have a moment after 1 meter. But in this case, I don't have my moment. And for this load description, you can either describe it or leave it blank. Therefore, you can, sorry, this spelling was not right. Therefore, you can proceed the same way or leave it blank. It does not really affect anything. After inspecting and observing that my model is good, hope you remember what we did with density. Once I add 24 and I go to loads, it is going to add my dead load. Therefore, it means I'll have factored the dead load twice. But I could delete this because I factored the dead load in my calculations. Therefore, I have my beam there and all my loadings are as stated. And then, of course, downward loads are stated as positive. If you have any upward load, let's say we want to do this as negative, you can observe what happens. It will be stated as a negative load for span 1. You see, it is negative, therefore it will be calculated as an upward load, but for in this case it is downward, so it's positive. Having done all this, if I want to do my wind, if I want to enter parameters of wind, here is where I do the parameters, and then I enter the span number and the moments that are being caused by my wind in all the spans, assuming I have wind going in this direction. So I could have a different moment here, different one here, different one here, and there. So this is where I enter all that, and then as I proceed with the design. So but in this case it is a basic beam, we are just doing normal analysis. So after entering all that, then you proceed to design. In design, the first thing you get is these deflection graphs, and then they tell you your maximum deflection is 4.332 millimeters, and it is happening at 9.35 meters from the beginning. So you should look at that 9.35, which is here, and my maximum deflection is actually happening at this point of the edge of this cantilever. And then these, of course, these are elastic deflections when I load alternate spans, and the values are here. And then for long-term deflections, the values are also here. For moments and shear, these are my diagrams, these are my shear values. My maximum moment is negative 51.12 kilonewtons happening at this point, and then my maximum shear is also 70.66 happening at 1.15 location. And then as I shift these, I'm also able to observe as these others are shifting. So you can get your maximum moment here and your maximum shear force from this drawing. And then for reinforcement, I have not provided any reinforcement, so I have to provide before I come and check. So after ensuring your analysis is good and you wanted to just leave a stop at analysis, you can stop here, and somebody else will design, or you design later. But you can observe from reinforcement, even if I have not provided, it gives me the maximum area of steel required, which is this at this location, and the maximum shear links required, which are this at the beginning of my beam, which is at that location. And I can proceed now to do my reinforcement. Once I get here, I need to do the beam type. There are different beams. It is either a normal beam, a slab beam, a flat slab, or a flat slab with a middle strip, or a rib. So it is just a normal beam, you just enter 1. My maximum bar length in Kenya, we normally do 12 meters. This will help when they want to curtail the bars, as some drawings will be generated the way you'll observe. And then you have top bars, the ones you prefer to have in your system. You have top, minimum bar diameter, and maximum. So minimum I state to be 12, and for maximum in my country is 32. But also you should limit this depending on the beam you are designing. For instance, in this beam, I want a maximum of 16 millimeters, so that is what I'm going to indicate here. And then for the minimum, it's 12, and then I'm also going to go for a maximum of 16 millimeter bars. I would do that. If I'm getting very many 16 millimeter bars, then I will increase the bar diameter to maybe 20 and design it afresh. And then minimum star-up diameter is 8, and the maximum 16 is too big for my star-ups. Maximum, I'm going to say the maximum is 10. And then the shape code, there are two shape codes here. There is shape code 72 and there is shape code 60. So you are the one to find out the one that works in your country and where you are, and go with it. And then the first bar mark, because the marks are given bar marks, you can either use alphabet or numbers. So for me, I normally love using numbers, so I go with 0, 1. And then the first bar mark at the middle and the bottom, they are optional, and I don't really like inputting them. The same way the software has left them, I find it good that way actually. And then you have cover to your star-ups, the top cover, the bottom cover, and the side cover. Now remember, in the beginning, while we were doing our input parameters, we did 40. This one was just preliminary. So here we're going to do the actual cover of our beam, and I'm going to state I'm having a beam cover of 25 millimeters. Then 25. And then minimum startups as percentage of nominal, you leave it at 100, though you can change it if you wish to change it, but normally I leave mine at 100. And then you have the loose method of detailing. This is the way Prokon details your element. I would love to see that, so I leave it as N, and the rest I leave it just the way they are. And then I proceed to generate reinforcement. Now in generate reinforcement, it has taken the area of steel that was required, and then it has given me the maximum steel that I can use, the steel that I can use here. And then the bars that are red are the ones that are selected at that moment. So I can do two 12mm bars at the bottom. Then you see this is a full bar, and then at the top I can do 12mm, but where I'm having these cantilevers, I'm required to add 2 more bars at these supports so that they can take care of the cantilever action of the beam. Therefore I have been able to design this, and I can even generate the bar bending schedule and look at how it appears. So if this is okay, I can move to startups, and then you observe the startups that I'm having in my system. This depends on what you chose when you are doing this 72. So if I choose 60 and I generate reinforcement afresh, look at how your startups appears, and this is actually the most common in my country. So depending on what you prefer in your country, this is what you do. And then for shear reinforcement, I'm seeing here they have been provided. There they are. The spacing is 250, and then of course they have given me the lengths and all this. And then I can have sections of my beams. You see sections have been taken at different intervals, and here is a 3D of my beam. Yeah, so I would love to move it around. Let me use this. Yeah, so this is how my beam will appear on site. Hope you remember the extra 2 bars that we were adding. And from detailing, because the beam size is 200, if you do this, you're not going to have enough space for your concrete to pass through. Therefore you're going to have internal honeycombs in your structure. But once you're detailing, you should ensure you detail this the correct way. And yeah, so here is my beam. You can see how it has been tied. Yeah, so from here you can proceed to bar bending schedule if you want to generate it. Then you can say generate schedule, and of course yes, so it will generate the schedule, and you can be able to open it from Prokon pads to observe it. But here is just sections of the beams and the way they have been generated. And lastly is if you want to now print your work, you proceed to calc sheet, and then you observe all these things here. And then you can change this. You just right click, then you right click on your title page, these title block, and then you can edit header. So you can enter various parameters here. Job number 01, job title we can say student, or let's say Bromtech. Bromtech, client is the student, and then calculated by, this is engineer Onsongo, and then checked by, this is engineer let me use one of the engineers from our office. This is engineer Roy, and then the date today is on 26th of May, and this is the 2023. So you say okay, you see it's here, and then you have your parameters. You can go to output settings, you state what you want to appear. Just go through it slowly by slowly. If you click on everything, it is going to print almost everything that you have worked with. You see, I have all the parameters that I did in the input tables, and then here are the sections that I did. Here are my spans, here are my supports, and then my loadings are here. If I did the load description for all the loads, they could have appeared here. Then of course the sections that I selected, the elevation of the beam, Then I have my diagrams there, BMD, SFD, steel diagram. Then I have these crack section tables. Then they're quite a number, so you should not just print everything. Find out what you want and what is really necessary, and then yeah, so towards the end it has even given me these reinforcement tables and all these things. So if you want to get the diagram, and then you see I have these my reinforcement whatever. So if you want to get the sketch of the beam, you can go to Prokon pads where we had saved it, and you can get it from there. But for now, I believe you have been able to see how we have designed, and we got two T12 bars at the bottom and two T12 bars at the top, with extra 2 bars at the cantilever ends. So thank you, and I think then you can go to print now if you want to print it, and then you say okay. Then how do we call it? Let's call it Prokon beam 1 practice. Then you save it, so you can go to your desktop. If you've saved it in the desktop, it is here. Then see, so you can submit these to the detailing engineer or to the draftsman, or for local authority submission and all that. Therefore I believe that is the end to designing of a beam in Prokon. Continue staying in touch. We have also done this beam manually. We have used other softwares in design of this beam, so that at the end we can compare whether the values are really matching, and whether these softwares are helping us, and how to optimize our designs. Thank you very much, and may the good Lord bless and keep you. See you next time.